ethylene and propylene. The ethylene and propylene in the industrial they call olefins. So both reaction is occur at 750 Kelvin at 1.2 bar. Only two reactions occur in this case. So they want to know if the reaction reached equilibrium already, what is the product composition. So the meaning is you have to solve for the reaction coordinate, then you can determine the mole fraction of each. So when you have chemical reaction, you think of the equilibrium constant, and the equation of the equilibrium constant gives the Fourier fraction. So at first, in this case, you know the temperature, so it means that you can calculate for the equilibrium constant directly. As it says, equilibrium constant is separated for each equation, each chemical reaction. So in this case, you have reaction number 1 and number 2, then you have two chemical equilibrium constants. So the first one, you can calculate using the equation that you have learned before. It's the same for today. So the equation 1, you at 750 Kelvin, you have the equilibrium constant equal 3.8156. And for the number reaction number 2, you have the equilibrium constant which we call 268.4. So these two will be used again, combined with the fundamental equation that we have known. So in this case, they assume the ideal gas state. So the equation from the fundamental one is reduced or simplified into this one. So the Fourier coefficient in solution have already eliminated because it's equal unity. So the equation is in this form. You have two equations. You have two reaction coordinates separated for each reaction. And for the reaction 1, you have the stoichiometric number equal 1. And it's the same for the reaction 2. The total stoichiometric number equal 1 as well. So you can write this equation into two equations based on each reaction. So I just clarify the mole fraction of each species in equation 1, which is the ethylene, ethane, and also the butane here. And this is the total stoichiometric number. 1 minus, so it becomes minus 1. And the same with the second equation is this propylene and methane and mole fraction of butane. The K1, K2 here you have already determined in previous. The P standard pressure here is equal 1, and you know the pressure. So actually these two equations is not much difficult. The first thing that you have to do is you have to write the mole fraction of each species into same parameter, which is the reaction coordinate. So if it's on 1 mole of the normal butane feed, so it means the initial total mole number in the system is equal 1, which is the butane. So in the case of butane, you can write the mole fraction is equal to 1 minus is come from the stoichiometric number here, reaction coordinate reaction 1, and minus from the stoichiometric number here, time with the reaction coordinate number 2. For the denominator here is equal to the total initial mole number in system, which is equal 1 from the basis here, and plus with the reaction coordinate for reaction 1, and plus with the reaction coordinate for reaction 2. For the other components, you can write the mole fraction in the same manner. For the reaction 1, the mole fraction of ethylene and ethane will be equal in this one. And for the reaction 2 here, the mole fraction of propylene and methane will be equal into this one. So right now you have clarified each mole fraction in terms of the epsilon 1 and epsilon 2 already. So you can see that if you put back into both equations, rearrange a little bit, then you can solve the equation. So I have substituted all the mole fraction in the previous slide into this equation. So you get the equation A here. Again, for the second equation, substitute all the mole fraction in terms of the epsilon 1 and 2, then you get the number reaction number B here. It still look very complicated to solve. So in order to simplify it, I divided the equation B here with the equation A here. So you can see that the denominator here is the same, is very same, and the standard state pressure is also the same, and pressure is also the same, so it can eliminate very easily. And if you rearrange a little bit, you take the power of 1/2, then you get the reaction coordinate for the reaction number 2 equal to the fraction of the equilibrium constant for reaction number 2 over the equilibrium constant of reaction number 1. Power with 1/2, power with 0.5, and time with the reaction coordinate for reaction 1. So now you have the you can write the epsilon 2 in term or in the function of epsilon 1 only. So if you put substitute that into the equation, then you have only one parameter. So I have substitute this equation back into equation 2. Then you get this equation. Just rearrange a little bit here to get the left hand side term equal to only the epsilon 1 here, and I also change the fraction of the equilibrium constant for reaction 1 over reaction for reaction 2 over reaction 1, power with 0.5 into the symbol of kappa here. It's kappa. So it's up here in here. So the kappa here actually is equal to this fraction. So now you have two equations, two unknown parameters. You know the equilibrium constant for both reactions, then actually you can calculate the kappa. The kappa is the constant, in this case, at the constant temperature. So you calculate the kappa here, which is equal, I just substitute the value back into this equation. So if you use the calculator, you can get the number 8.342. And now you can see that you can calculate the reaction coordinate for reaction 1 as well. So you know the K here, P, and the kappa, then you can calculate for the reaction coordinate of the reaction 1. If you put all the values in the calculator and calculate it, you will get the number of reaction coordinate equal to 0.1068 for reaction 1. Then you know that the reaction coordinate for the reaction number 2 is equal to the fraction here. Don't forget to count with the epsilon 1 here. So it's different from the kappa here. they have this function. So substitute all values here, you can get the reaction coordinate for reaction number 2, which is equal 0.9. Now you know the reaction coordinate for both equations, for both reactions. Then you can determine the mole fraction for each species. So this one you have only two chemical reactions. You can see that it's not much complicated and it's not much different for what we have learned in the previous simple reaction system. The complicated is added for the number of chemical reaction that is added. So the unknown parameter of the reaction coordinate is added, but the unknown parameter increase, the number of unknown parameter increase with the number of the equation. So in the principle, it can be solved directly. No complication here. But however, this is a simple exercise, simple example here. Because you know the temperature, then you can calculate for the equilibrium constant directly. Then the unknown parameter here is only the reaction coordinate for each chemical reaction. So it is simple. But what if you don't know the temperature? This means that you have another unknown parameter, which is the temperature. You don't know the equilibrium constant. Directly, you have to guess the value of three unknown parameters. With three unknown parameters, you will have two equations from the equation of chemical reaction equilibrium, and another one equation is come from this one, the equation of the equilibrium. It's the same with the workshop that we have done in previous lecture. Okay, let's see another exercise which is a little bit more complicated, and actually we will do the workshop for the calculation using the spreadsheet for the example in next week. The next week we will use the spreadsheet to solve this one, this exercise 2, and we also have another exercise for the multi-reaction equilibrium as well. As I have ever said about the method that's called if energy minimization. So, and if you remember the lecture that I have said about the criterion for the chemical reaction, I said that actually we have two methods to do to calculate the equilibrium of the chemical reaction. One way is the equilibrium constant method. It generally used for the simple reaction, and it is the method that we've done so far. I mean, we use the equilibrium constant to calculate the reaction coordinate. And actually we have another method that we just have to minimize the given energy, and we solve for the reaction coordinate that can get the minimum value of the energy. In that case, we call the minimization of the energy method. So that method is generally used for the multi-reaction equilibrium, which is now we dealing with. So for the exercise 2 here, I will still continue to use the equilibrium constant method to solve the problem, and you can see how much complicated by using this method. You can use it well, but it's not popular to use for the multi-reaction equilibrium. And in the next lecture, we also see another method to solve when you have multi-reaction equilibrium. This may be easier. Usually it's easier when it depends on individual as well. So let's see that exercise 2 here, and we will use the equilibrium constant just to solve the problem. For the exercise 2 here, they just said that they have a base of coal, which they assume to be just pure carbon, a solid pure carbon here. And a coal here is gasified using the steam and air to produce the gas steam, which containing of the hydrogen, carbon monoxide, oxygen, water, carbon dioxide, and nitrogen. Nitrogen is come from the air that gets into the system. And they say that in the freeze to the gasifier consists of 1 mole of steam and 2.38 mole of air. They want to know the equilibrium composition, and if possible, just plot the mole fraction of each species versus the temperature that change into the system. So the reaction is occur at 20 bar, and they want to know the composition, the relation that change of the composition related to the temperature from 1000 to 1500 Kelvin. So they also provide the standard if energy change for this reaction at each temperature as well. So this for each species, water, carbon monoxide, carbon dioxide. Do you wonder that why they don't provide for the hydrogen, oxygen, and nitrogen? Because it's the same procedure that I show you to determine the number of chemical reactions, the number of independent chemical reactions. When you have the mixture of many components and you want to know how many chemical reactions, in that case you have to start with the procedure of writing the formation reaction. And in that case, when you writing the formation reaction, it is for the compound only. Compound is meaning only the carbon monoxide, carbon dioxide, and water in this case. The hydrogen, H2O2 and N2E is considered as the element in the formation reaction. So actually when you write the chemical reaction for this system, the hydrogen, oxygen, and nitrogen is not made for the calculation. So in this case, they just provide the 3 components here. And what they give us is the standard state if energy change or formation of the species at each temperature. What's the useful of this information? How do you use this parameter to determine what parameter? Equilibrium constant, right? But the very generous of this example is usually when you calculate the equilibrium constant, you calculate you use the standard if energy change at the reference temperature. If you remember, at the reference temperature with the substitute 0 here. And you just add another term for heating, changing the temperature from the reference temperature to another temperature of the reaction temperature. And you just add that effect to the for changing the temperature from reference to the reaction temperature. So, but in this case, we done this so far because usually in the practice, we don't know that if energy change at any temperature. The data that we have is at the reference temperature. That's why we have to use the long equation to determine. But in this case, from the definition of equilibrium constant, exponential of the fraction of the minus standard if energy change over RT here. If you know the active energy change at the reaction temperature already. You can calculate the equilibrium constant there. But normally you don't know the standard heat energy change at the reaction temperature. You know the data at the reference temperature. That's why you have to use the long equation to calculate the equilibrium constant. But in this case, actually they have already give you the standard heat energy change of formation at the reaction temperature already. So the method is you just summation weighting with the stoichiometric number of each species for each reaction, then you can calculate the equilibrium constant using this equation directly. You don't need to use the second one. You can use the short equation heat directly. So this is the general from general data from the example here. But it seems that the problem is you don't know how many chemical reactions that can be occurring in the system. So it seems that you have to determine that first. They said that in the phase system they feed 1 mole of steam, 2.38 mole of air, right? So just determine how many mole of oxygen and nitrogen that it gets into the system. So 2.38 mole of air containing of oxygen is equal to 21%. So in this case, if you calculate for the mole of oxygen, it will be equal to 0.5 mole of oxygen, which is placed into the reactor or rectifier. Same with the nitrogen, you just count 0.79 with the 2.38 here, and you get 1.88 mole of nitrogen is placed. Then you have to determine how many independent chemical reactions that can occur in this system. You can do the same, which is the first step is writing the formation reaction for every compound that exists in the system. In this system, the compound is only hydrogen, carbon monoxide, and carbon dioxide. So you just need 3 formation reaction for 3 compounds here. The first one is the water. It comes from hydrogen react with half mole of oxygen here. The number 2 and number 3 is the formation reaction for the carbon monoxide and hydrogen. Can you try to write it? So for the carbon monoxide, it comes from carbon atom react with the oxygen gas, right? And if you determine the stoichiometric number, it should use only half mole of oxygen here. Same with the carbon dioxide. So it just use the carbon atom react with the oxygen, and this one is just use 1 mole of oxygen. You can get the carbon dioxide. So the second step is you have to eliminate the elements that is not present in the system. In the previous example, for example, it is the carbon and oxygen, right? But in this case, both carbon and oxygen are presented in the system as well. So in this case, hydrogen, oxygen, water, carbon dioxide, and carbon dioxide. Every species are presented in the system. So actually, these 3 reactions is a set of independent reaction already. You don't have to do the second step. This means that now you know the number of independent chemical reactions that can occur in this system already. When you know the chemical reaction, then you can calculate the equilibrium constant and also write the equation of the mole fraction, pressure, and equilibrium constant. So that is the next step that we will do. So from the fundamental equation between the fraction of the viscosity and Coulomb constant here, then you can separate for the three reactions. The first reaction is the fraction of viscosity of water divided by viscosity of oxygen and hydrogen. Don't forget to power with the Schwarzschild number of that species as well. So in this case, the oxygen here should be powered with 0.5. And same with the reaction number 2 and number 3. So in this case, you have to find the viscosity of water, oxygen, hydrogen, carbon monoxide, carbon dioxide, and carbon. And the carbon is the solid state, the solid carbon, the whole. So usually the viscosity is related to the pressure. And in the case of solid state, the effect of pressure on viscosity is very small. Right? For example, if you change the pressure, the volume of the solid compound, solid element will not change much. So in this case, we can assume that the fraction of viscosity for the carbon atom is unity here. It will be an error, but it's very small, and we can assume that it can be negligible. So in this case, we assume that the fraction of the carbon in solution over by the fraction of pure carbon at the standard state is equal to unity, and when it becomes unity, then we can only form the reaction. And another species uses the relation between the mole fraction, viscosity coefficient for the gases, or mole fraction and activity coefficient for the liquid state to change the viscosity in solution. Okay. So in the case of water, just change to the mole fraction and fraction. In this case, in this sample, they use the ideal gas assumption. But if you can see from the pressure of the system, actually it's very high. It's 21. Actually, it's not justifying much to use the ideal gas assumption here, but I think just for the seeing the procedure to calculation, and as I said, usually the method of the Coulomb constant is not popular to use for calculation of multivariation, because it is very difficult if you don't use the assumption of the ideal gas assumption. You have to calculate the viscosity coefficient. You can do it as well, but it just adds another task for calculating the viscosity in solution to the work that we have to do. So in this case, just see how to solve the problem. So in this case, just let's assume that the ideal gas state can be justified for this example. But in my opinion, I think ideal gas assumption is not appropriate assumption for assume in this example. But if you use the ideal gas assumption, for this example, the viscosity in solution here can be negligible because it will be equal 1 here. So the viscosity in solution here will change to only the form of mole fraction in gases times with the pressure here. And you rearrange the equation a little bit, then you can get the remaining equation here. So again, the mole fraction in purple term here is neglected already because the pressure effect on the viscosity of solid is very small. The fraction can be assumed to be unity here, so it's negligible. And this one is changed to the standard state pressure and also the mole fraction. it's like I have it's like what we have done in the previous example. So you just list all the mole fraction, list all the frequency ratio, and then you can eliminate the standard state equation together, and then you get the final equation look like this. Okay. Now you have three equations. Yeah, you have three equations, and actually you can determine the Fourier constant for each equation as well. So, if you write change the form of mole fraction into the function of equilibrium reaction coordinate, then you can solve the equation. Solve this example. Let's just change the form of mole fraction into the function of reaction coordinate first. So it's the same procedure that we have done so far. First, I have determined the total stoichiometric number of each equation first, each reaction first, which is called like this, and then the initial total mole number of each species is equal. So at first they have 1 mole of steam, right? And with the 2.38 mole of air, you have 0.5 mole of oxygen and 1.88 mole of nitrogen. And for the product here, you don't have any initial mole in the system here. So in the case of mole fraction of hydrogen, it should be equal. Hydrogen is present in the reaction 1, only 1. So you have the reaction coordinate for reaction 1 minus reaction coordinate 1, and over with the total is equal 3.38, and cut with the reaction coordinate of each equation. So the mole fraction is like this. In the denominator here, the reaction coordinate for the reaction number 3 is not exist because the total stoichiometric number for the reaction number 3 is equal 0. So you can see that only reaction coordinate epsilon 2 and epsilon 1 is appear in this system. Okay, so in principle, if you substitute all this mole fraction back into the equation, the beginning equation that we have, you will get very complicated equation look like this. In this case, I just made it more simplified to see by changing the group of this parameter into the symbol m here, and m is appeared here, like this. So I change this group 1 into m here. Then in principle, you have 3 unknown parameters, which is epsilon 1, 2, and 3, and you have 3 equations. So in principle, you can solve it already. But if we just look a little bit into this system, for example, at 1500 Kelvin here, I try to calculate the value of the equilibrium constant for each reaction. And at this temperature, for example, at this temperature, I get the value of the equilibrium constant is equal 10 power 6, which is very, very large. And for the reaction number 2 and 3, you get the value of the equilibrium constant equal to the much up to the 10 power 14, which is very large value. From this estimation, it means that the equilibrium constant are very large, It means that if you look back to these three equations, it means that the denominator here uh, in each equation must be very very small. So that cause that when the denominator of the fraction is very small, then you can get a very large value of the equilibrium constant in these three equations. And the meaning of the very very small in this case is seen that the term here, the purple term here, might be must be nearly zero, must be nearly zero. So the meaning of the purple term here, close to zero, is mean that probably the mole fraction of oxygen in the equilibrium mixture must be is very small as well. Because if you can see this term and this term, if this term is nearly zero, it appears in here as well. The epsilon 1 and epsilon 2 here, and epsilon 3 here. The numerator in this fraction must be very, very small if it is nearly zero. So in this case, they just reformulate the problem again by eliminating the oxygen species from the equation. So as first they just use the formation of compound reaction, formation reaction of compound to determine the number of chemical reactions, and they get three independent chemical reactions here. But when they form the equation in this slide and they check the equilibrium constant for each equation, again they found that the denominator of each equation must be nearly zero, and that means the mole fraction of the oxygen must be very small in the mixture. It might be that the mole fraction of oxygen, it means that the oxygen might not be exist in the equilibrium mixture. That is the meaning of it. The oxygen might be not exist in the equilibrium mixture. So that's why they reformulate the problem by eliminating the oxygen from the equilibrium mixture. In this case, they just use the starting three equations here. Sorry, I have to pick up the